Hello everyone. Today we're going to take a look at various kinds of numbers. So there are numbers that we use for counting, for solving quadratic equations, and one of these quadratic equations made one of different types of numbers which are called the complex numbers. We're going to take a look at that too. So without further ado, let's get started. So first we're going to take a look at natural numbers. So what are natural numbers and what's so natural about them? So, as you can see from the name, natural numbers denote to the fact natural. So, whatever you can count naturally is natural numbers. So, whatever you can count naturally are called natural numbers. Apart from that, we do have another set of numbers which are rational numbers. So, there is also a counterpart of this which is called the irrational numbers. We'll get into these details later on. And also there are another kind of numbers which are just one step bigger than this set of numbers, which are called the whole numbers. So what are natural numbers, what are whole numbers, what are rational and irrational numbers? We'll take a look at them using Venn diagrams. What are Venn diagrams? Venn diagrams are basically circles which maps the sequences and domains of various kinds of things. What I mean by that, for example, if you map a boundary of an object, for example, this is field A. So let's say you draw a bigger field outside of it, which this field is a part of. So when you say that, these are called Venn diagrams. I hope you know this, but it's fine if you don't. So field A, and now there is a bigger field B, and field A is inside of field B. So what you say in these cases is that field A is enclosed by field, which is in this case B. Right. So taking this into fact that you can obviously see that this is field B. So this entire outer circle is the field B, and this is field A, which is inside of it. Now you can draw another field, which is the smaller one, but it's not part of field A. It's part of field B. This is some other field. So you can call this as field C. Now field C is not a part of A, but field C is a part of B. So how do you denote that which is a part of what? So if you take these as sets, so in maths, whenever you have to mention a field, in the sense like an area or a domain of numbers or objects, well defined objects, what you do is name them as sets. So all of these have some elements inside of it. So sets have elements inside of them. So elements, ordered sets are always ordered, so there is no redundancy. There is okay, so there is no redundancy, and which basically means there is no duplicate copies. No duplicate copies. So for example, if you were to make a number, if you were to make a set of the word, let's say New York. So the word New York has NEWYORK. So this is a set. So these are the set letters that are in the set, in the word called New York. But for example, if you were to take a word, for example, apple. So if you were to make a set of all the elements that are in the word apple, so you'd have to write A, comma P, comma L, because P is already mentioned once, and then E. So this is these are also A is an element in the set which contains all the letters of the word apple. So how do you denote this in numbers? So you can say that the set of the word. For example, let's take something else. Uh, let's take guava. So you notice there are two A's, right? So when you say, let's say a set S contains, so set S is a set, so you can write this S equals, and then second bracket or a curly bracket or braces, whatever you call it. Then you start writing from the left, G U A. You put V, and you notice A comes back again. So A is also already mentioned in here, so you don't mention A again. So these are the elements that are in this. So the S is the set containing all the elements, all the words as elements in the word guava. And how do you mention, for example, that A is a part of this set called S? So you say A belongs to the set S. Right. This is not S in the sense, this is a set S. So I'm writing it this curly braces. So yeah, A belongs to S. Now, for example, there is another letter, which another word, for example. So you say that letter word has guava, um, uh, guava juice. So notice this is a much bigger word. So if you were to make a set of this, so let's say this is set one, there is set two, and set two has the following words: G U A V J U I C and E. So this is another set. Now notice that some of the words G U A V are already in this. So if you were to distinguish between S1 and S2, you'd have to say that this is a. You can obviously see that S2 is much bigger than S1, and there are more elements than this. So you will say that S1 is smaller because it has four elements. So it has lesser number of elements. So you can say only four elements. This statement is not really necessary, but yeah. Now, how do you mention the relationship between S1 and S2? So you can see that all of these elements can be found in this. Plus, there are some more things that are in this set 2. So what you can say is set 1 is a subset of set 2. So this is how you mention a subset. Apart from that, if you have, which can be great, so this is like greater than or equal to. So like S1 is lesser than, but just in case of lesser than, because this is a set, you mentioned like this with a curly C kind of a thing, then you write the bigger set. Now, for example, there can be sets which are comparable, but one of them may be bigger or equal to. So you write like this, B1. So you write it like this as B1. So when you are done with that, so you can say like A1 can be an equivalent set or an equal set, which we will not cover in this. There are two types of equivalency. There's one equal and equivalent, which basically means that all the elements are same in number, and all the elements are same, plus all the elements, the number of the elements are also same, and the elements are also same. So yeah, that's equal. The equivalent is like the number of elements are same. So A1 is equal to B1 can mean both of these. You have to specify which one it has. All right. So other than that, we're talking about redundancy, so which got us into set theory. So the sets need to be have elements and they need to be ordered. There is no redundancy, and so no duplicate copies. Now, how do you mention it this? So you see, field A is not related to field C. So you can say, for example, if you consider this to be a set of something, you can say A is a set, and if you find the common, this is called an intersection of sets. So what intersection means is that you try to find the common elements between both the sets. For example, set 1 has 1 2 3, and set 2 has 4 3 and 2. So if you do intersection of a1 and a2, what you will get is, which is the common, is 1 is not a common, 2 is a common because 2 is also here, and 3 is also common, so 3. So you'll get 2 and 3 as the intersection. There's another thing which is called union. Union is pretty similar. You just merge both of the sets and remove the redundant ones. So here you have 1 2 3 4 3 2. So you write 1, which is accounted for. Now 2 are in both, so you write it once. 3 4. So you write common, you join both of them together. You merge both of them. So one is merging, another one is finding what's common between them. So if you try to find what's common between A and C, you'll notice that there is no space between A and C that is common. So you will write this as a null set. Null set means there is nothing in this set. So absolutely nothing in this set. If you were to find the intersection between A and B, so A and B, whatever, so as A is completely bounded by B, so you'll have to write this as A. Why this works? Because see, so B is a bigger set and A is smaller than this one. When you have B and A together, so it's asking what's common between B and A. So entirety of A is inside of B. So the entirety of A is common between both of them. A has already itself, and B has the entirety of A. So this is like company A, company 1 and company 2. So if they ask you what's common between company 1 and company 2, is that company 1 is common between both of them because company 1 is owned by company 2. If you were to find okay, so if these two things are done, this is very pretty easy to understand, like because A is intersection of, and A and intersection of C, there is no common point between A and C, so they are completely disjoint, so you call them disjoint sets. Right. So since we are done with this brief introduction to Venn diagrams, and so we can move on to defining how do we define numbers. So we can move on with first of all natural numbers. Natural numbers are the counting numbers. So when you start counting, for example, there is one guy. So you say this as one person. That's how you start to count. Now, subsequently, when you move 1, 2, 3, 4, 5, and you go on with that, that is called natural numbers. So natural numbers is denoted by this n looking like character, which is equal to 1, 2, and so on. Now whole numbers. Whole numbers are, so there's a debate going on for mathematicians that whether natural numbers should count zero in it or not. But for sake of simplicity, we'll not go into that debate. We'll define whole numbers as this W looking sign, which is it has an extra element added to this, which is 0, and then you continue with the same thing. Okay, so these are very simple definitions. Now, if you want to move to rational numbers, so what are rational numbers? Rational numbers are defined in a pretty easy way. Say, if you wish to take a number which is a fraction. For example, if you wish to divide two numbers from the natural number, what happens is that if you apply a binary operation like division on this element, so if you want to extract an element, say x belongs to natural number, and you also bring another y which also belongs to natural numbers, you are extracting two elements from natural numbers. They can be anything, and now you wish to divide them, x by y. Not every time you will get this x divided by y. Sometimes you can get, like for example, 2 divided by 1, 4 divided by 2, 9 divided by 3. These give you subsequently 2, 2, and 3. So these things are inside of natural numbers. So these are fractions. These have all 1 and in the between, but these are also natural numbers. Now sometimes you'll get fractions, something like, for example, 9 by 2. So when you get the answer of this, this becomes 4.5 or 4.5. So 4.5 is not a part of natural numbers. So where do you keep this number? So this is the need of defining rational numbers. So where do you keep this? This is a fraction. So where do you keep a fraction? Because fractions are not a part of natural numbers. So what you do is define another set of numbers which are, there is another set of numbers which are called the integers. Integers are defined with z. So now integers are defined as all the natural numbers and 0 or the whole numbers. So the whole numbers taken together and the negative signs of them. So you write this as, for example, 0. You start with 0, 1, and you go on like this. Also, you add the copies of this side too. So that basically means it's minus 1, 0, 1, 2, and go on. And this is the negative side of the numbers. So these are positive and negative numbers together. If you write this symbol, z plus, which means positive integers. Why z? Okay, so the z word comes from a German word which is called Zahlen, which means to count. So once you have positive numbers defined in here, positive integers defined in here, you'll notice that positive integers which start from 0 to infinity. I'm not writing infinity because infinity is not a number, it's a direction. So you go toward positive infinity. So these z and w are the same. So they are the same sets. They are the same sets. So sometimes positive integers and whole numbers are used interchangeably because they are both the same. So yeah, they are the same numbers. Hold on, I'm checking on the stream 1 second. Yeah. So really sorry for that. Uh, so yeah, uh, the positive integers are equal to equal sets with whole numbers. Now, there is two words for this. There is one thing called cardinality, which you might be getting on your courses. Cardinality is same, and the elements are same too. So what this basically means is that not only the number of elements in positive integers, which are 0. So 1 second, I'll write this for you. Which starts from 0 to dot 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 dot. So it starts from 0 to infinity. This also starts from 0 to infinity. And also the elements, which is 0 to infinity and 0 to infinity. Both of them are same. So that's why you have the number of elements are the same. Whatever this is one set of numbers. You define this later as aleph null number of elements. You define this as do the same thing. But see, that's not the point. The point is that both of them have the same number of elements and the elements are also same. So that's why they are called equal sets. Now, you may ask another question is that are natural numbers a part of the whole numbers? Yes. So the natural numbers are a subset of the whole numbers. Why? Because the whole numbers are bigger than the natural number with one more element. So if you have the number of whole numbers which is starts from 0 to infinity, this has one more element which is 0. So you cannot write this. You cannot write this. So this is not true, but this is true. Right. So moving on, the problem that we had is how to define rational numbers. Since you have positive integers, we can also write this as negative integers, or you can write this. These are various ways of writing it, but I'll not go into the details because it varies from books to books. Rational numbers are defined as, say you pick up an integer from the set z, and you pick up another integer from the set z. Now you decide to divide them. Quick fact is that q should not be 0, because if you divide by 0 there is no meaning to it, because this whole fraction becomes undefined. So this is a statement you're writing. You're picking up one element from integers, you're picking up another element from the integers too, and now you decide to divide them. And one of the q should not be 0. It can be negative though. So how do you make this set? So this is technically, this m in here is the element of rational numbers. So how do you write this? So rational numbers are denoted by q. So q equals m such that m equals p by q, where p comma q belongs to uh, integers, and you can write with and q not equal 0. You can write this, or you can write it in simple terms, like if p belongs to integers, q belongs to integers, uh, assume m equals p by q such that q not equals 0. So whatever number this m is, for example, if you take p equals 1, q equals 7. So 1 by 7 is m now. So this m goes on to this set called q and puts this in the set. So yeah, you can write 1 by 7. You can write, for example, now you take this is a constructing of a set. What we are doing is constructing the set called rational numbers. So yeah, now you can write p equals 2, and you can write another number q equals 8. Yeah, so you can write 2 by 8 equals 1 by 4, which is also a fraction. You can take p equals 0, q equals 2, that gives us m equals 0, which also goes in the rational numbers. You can take another example of p, let's say any negative integer, for example, -7, q equals to be 2, so -7 by 2 is m. This also goes in this. So whatever you can construct with this set of rules is a rational number. Yeah, I think we're done here. Yeah, this is written with Q. Now there is another question you may ask, that what happens when you, not all the numbers are fractions. Some of the numbers look like this too. So what are these numbers? These numbers are called irrational numbers. Irrational numbers. Why are they called irrational? Because they have no sense. No, not that. But yeah, irrational numbers are called irrational numbers because they cannot fit into the rationals. Because you can never write this as a fraction. The value of root 2 is 1.414 and dot 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 dot. It goes on. A very famous irrational number would be pi. And goes on. Yeah, so it seems like I'm writing someone's phone number. You can write E, which is a very common example. This is called the Euler's number. This is also irrational, and there are other numbers which are also irrational, but that's for a later thing. But whatever you cannot fit in rational numbers and not complex numbers are called real numbers. But how do you define them? So the definition of irrational numbers is pretty hard to define now, but I can give you a general sense of how irrational numbers are defined. So irrational numbers are defined as something that is not a fraction. That's not a very good definition, but you can say they are. Oh, first of all, they are denoted by Q star. So they're denoted by Q star, and you can write the definition of irrational numbers once we move on to another set of numbers which are called real numbers. So now we must be working from another point of view, that we start here, then we move on to bifurcating this into these two. Now rational numbers get divided to natural whole integers. You can do that too. Yeah. So moving on to the real numbers, the real numbers are defined as to be the collection of these two things, rational and irrational. What do I mean by that? So whatever fractions you have, whatever negative fractions you have, and whatever is not constituted in this is a real number. So for example, -1/7 is a rational real number. Pi is also a real number. E is also a real number. So if I write this Q union with Q star will give you real numbers. I hope you understand the union sign. This means taking both of them and merging together. So that's the definition of real numbers is denoted by capital R. It's not an R actually, but it's a fancy kind of looking an R. So you might be saying, oh, real numbers, what's left? What kind of numbers are left after this? There are a type of numbers which are left. I must say one more thing is that rational numbers have two types, which are called terminating and non-terminating decimals. So terminating and non-terminating decimal expressions are expansions or expressions, whatever you say to be, are like, for example, 5 by 2. This gives you 2.5. So there is, you can add a zero in here, but that doesn't have, that's just a sense of precision you have, but it doesn't really mean anything. This literally means zero to the end. Non-terminating ones are, for example, 1 by 7. So this gives you a value of 0.412857, and this thing copies. So that is non-terminating. This is not terminating. It will go on. This value will go on. This value will keep on going 142,857, 142,857, and so on. So yeah, apart from that, you may have another set of numbers where the this repetition doesn't happen. That's what exactly pi is. That we don't have a proof until now why it's so it's pi cannot be defined as like this. You have a very bad approximation of pi, which is called 22/7, which is around 3.142857, and goes on. But see, the first two values match because pi is 3.14159265. It's a bit bigger than this. So what's the difference is that this is a fractional decimal. Pi can never be expressed as p by q, where p and q are integers. It can never be. That's the whole point of saying what pi is. Pi is irrational, and irrational numbers can never ever be defined as a fraction. That's the whole point of it. The whole point of it. Yeah. Moving on. So we moved on to real numbers. This is a very important definition because rational numbers are the definitions of rational numbers are the definition of very important for maths. And apart from that, whatever is not defined as rational numbers will go to irrational numbers. So whatever cannot be expressed as a fraction of two integers will become irrational. Now, moving on, we can take a look at a very special set of numbers which are called prime numbers. Then we can move on to different numbers which are not mentioned in here. Prime numbers. What are prime numbers? So, for prime numbers, we have to define the term called divisibility. What is divisibility? For example, 5 is divisible by 1 and 5 is divisible by 5. There is no other number in the whole set of natural numbers that can divide 5. Why natural numbers? Because not 0, 0 cannot be used for division because it gives you an undefined result, and also that zeros, we do not know how to divide something by 0. That's the point of it. And if you use negative numbers, that is true, but prime numbers, the definition of prime numbers doesn't include negatives. So, well, it does, but it's in a very different sets of primes. So yeah, 5. And then we have another number, for example, 18. So 18 is divisible by 9, 18 is divisible by 2, 18 is divisible by 1, and 18 is divisible by 18. So all of these fractions will give you something that belongs to the natural number. So these values belong to the natural number. Now you have this. Notice how 5 is unique. 5 has no number other than 1 which can divide it. But here 18 can be divided by 9, can be divided by 2, can be divided by 18 and 1, but these two are unique also for it. So how do you notice a prime number? So whenever there is a number, for example p, which is divisible, so how do you write the sentence? How do you write divisibility? Is that you take a number, for example 12, and it's like 3 times 4, right? So 12 is 3 times 4. So there are 12 can also be written as 12 times 1. These things are called prime factorizations. Why are they called like that? Because you are factorizing them, and you are trying to get so this is not a prime factorization, this is a prime factorization, because both of the numbers in here are prime and these are not prime. So how do you write divisibility? Is that, for example, for now you can write that 4 divides 12. This is not the backslash or the front slash. This is 4. This is a plain line. So this is like this. For example, let's say the definition of divisibility is that if 2 divides a number, say 16, so you write 2 divides 16. But if you have an algebraic equation, for example, x divides y. So this is not y by x or x by y. This means that whenever you divide y by x, this result will belong to natural numbers. That's the definition. Or if y is 0, this can also belong to whole numbers. If only and only if y equals 0. So prime numbers are defined as p. Every p, you can write this as capital P such that it has elements p, such that this is such that with double dots. Can you see this? Yeah. P such that write it a bit. Up here, P capital P such that P belongs P such that there does not exist X belongs natural numbers such that X divides P. It's a very bad definition, but I would say you can use it for now, which basically means that P and there does not exist X, like there is no number X, or there is no number in naturals which can divide X, which can divide p and x not equals to 0 uh, or 1. So that's the basic definition. Is what's basically saying that there is no x such that you can find it in natural numbers. For example, other than 0 and 1, there is no natural number, say 2, 3, and so on, that divides this number p. And we missed an x here, x which is p. So let's not define it this way. There's a very good definition of p. You can just write it like x as a number which is only divisible by itself and prime numbers. Yeah, I got the definition of it. Basically, you can write as such that n greater than 1, which basically means it's greater than 1 and 0, and uh, for all m belongs naturals, uh, m divides n implies m equals 1, or m equals n. What this basically means is that prime number is defined as n. All the elements in the set called primes will be defined as the element n, which is greater than or greater than 0. And for all numbers in natural numbers, there exists m. If m divides n, if there is an m that divides this small n in the natural numbers, that m needs to be either 0 or the n itself. Basically means that, for example, you bring out a number n and you find another number which is m, and this number is divisible, so divides n and gives you a perfect integer, perfect positive integer. What it basically means is that this m has either got to be equal to 1 or n itself, because that's what we saw in, for example, 19. 19 is divisible by 1 or 19, or for example, 23 is divisible by 1 or 23. So that's how prime numbers work. I hope you know what prime numbers are. Moving on, we can go to another different set of numbers. As I promised, we can go to the numbers called the complex numbers. But before that, we have to answer another question: is that if there is is there a prime number that is the final prime number? So, like, is there a set of prime numbers that is countable or uncountable? So, this set called P, which I just wrote, is it countable or not? So in set theory, you can definitely count a lot many things that are not countable or uncountable. But you can say, for example, that the number of primes are infinite. So there is no limit as to how many primes there should exist. There is no largest prime, you can say. So no largest. Right. I mean, you can prove this. If you want to prove, there's a very easy and elegant proof. I would say you start that proof by taking a prime number p. So you say let p be a prime number. Now the proof is all about there. This is a statement, so you can write this as W1 that does not exist. You can say something else. You can say there is no largest prime number. What this basically means is that you have to prove that there is always a prime number P2 which is always greater than P1 if this is the biggest prime number you have ever thought of. How do you prove this? So you start with this is a claim and this is the proof we are writing. Note that we can start by saying let P be unprime number, and now you find a way of defining this P as so the prime numbers before this can be written as like, so we must prove there is some prime there is some prime bigger than P. So we'll start by constructing a number called M. So what this M has got to do is that this M number is defined as every prime number that ever exists until P, and then you add one to it. Then you add one to it. Now, why this kind of a construction? Why this construction? Construction of M. Why are you constructing this M? There's a reason as to why we are doing this. It's possible that M is a prime number. So this is either possible that this M is prime. And what do I mean by this? For example, if this P, so if you were to prove that P is the biggest prime, so let's say if you tried very hard and you found out that the biggest P is 2, there is no more prime numbers other than, there is no more prime number bigger than 2. So if you put P in this, so you'll get like M equals 2 plus 1, which gives you 3. So 3 is another prime number, which fits into this algorithm's part. Now, what do you do for this case? So P equals 2 is the final prime number, which is proved to be wrong. So you go and move on and you take P equals 3. Okay, let's go. So if P equals 2 didn't work, we'll work with P equals 3. This might work. So you take M equals 2 times 3 plus 1 and you get 7. You notice that 7 is also a prime number. Is also a prime number. This falls back into this. You try it again with a different number. For example, 2 times 3 times 5 times 7. You go until 7 and you see it's 211. Yeah. You can go like this. You can keep going on like this. It either will be prime. So if M is prime, there are some numbers you will get for which M is not prime. You will not prime. So it's possible that M is prime. M is prime. It's also possible that there exists. So this is the M you're looking for. So this is there you prove it that there is one M which is one bigger than the multiplication of all these numbers. Since M is definitely bigger than P here. So you prove here that M is a prime bigger, but only if M is a prime, which comes out after this construction, bigger than P. What if this number is not prime? M is not prime. This is where the fun begins. So if M is found out to be not a prime number, what you can do is that you can consider a value of Q. So suppose that M is composite. So this is called composite. So you think M is a composite number. Sorry. So M is thought to be now as a composite number. So what happens after this is that you can say M is composite. It follows that M also has a prime divisor then, because as it's composite it has got to get a prime divisor. Let's say that divisor is Q. So we are introducing a new number called Q which divides m because it's composite. Now q can surely not be equals to 2, because if it is equal to 2, you can prove it to be like so if q equals 2, then m will be of the form 2 times whatever this set of numbers are, as x, 2 times x plus 1. So you can say that this is the general form of an odd number, 2 times x plus 1. So if you just isolate 2 in from here, m has all these natural numbers, 2 times 3 times go on. Whenever you are asked for, let's say there's a q, if you make a claim that q is dividing m, I can prove this wrong by saying that q cannot be equal to 2, because q cannot be equal to 2 and dividing m, because m is of the form 2 times something plus 1. If something is divisible by 2, it needs to be of the form 2 times something, and that's it. You cancel out the 2's and you get something. So m is not of the form, m is not divisible by 2. I can prove this. So that is, belongs like 2 times x plus whatever it is. So m is not so q does not exist if q is equals to 2. I can take similar claims for q equals 3. You can say like, what if q equals 3? Q as 3 divides m. That is also not possible. You can prove it by saying, let's say I pick up 3 this time and you write it's 3 times something too. So 2 and 5 and 7 and all of these chunks go into here, and you can say like, see, this is sometime something multiplied by 3 and it's added 1 to it. So whenever you divide this by 3, this will get cancelled, but this 1 will remain. So this will be a box plus 1 by 3 always. That does not belong to the natural numbers. So how do you move on with this? So you can keep going on until p does not divide m, as if you take m, it's of the form p times x plus 1, and q does not divide m when q equals p. Uh, so you can write this as, because this will not divide p, because this will not divide q, as p x by q will give you x, and this will always remain. So this is a part of the fraction. So you can say that these multiples are always staying. So let's start by writing the formal proof. So m, as we defined, as 2 times 3 times 5 times so on until p, you are finding a natural number called q, and you are saying, let's say q divides m. So if plus 1, so let's say if q does not divide m, if m is prime here, this can be two cases, as I said. If m is prime, then you generally prove that m is greater than p and m belongs prime. So there is a bigger prime. M is a prime bigger than p. And if m is composite, so if m becomes composite, you can write as m. If m is composite, you take another value called q, and you start dividing m with q by taking various options. For example, you can say q cannot be equals to 2. As I said, it will be of the form 2x plus 1. M is also of the form 2 times whole of this chunk plus 1. So 2 cannot divide 2 times something plus 1. 2 times 3 plus 1, which is 7, is not divisible by 2. It's not divisible. For example, also for 3, if you decide q to be equals to be 3, you can write the same thing. It's 3 times x plus 1, and for example 3 times 7 plus 1, which is 22, is also not divisible by 3. So you can keep on going until the point where q equals p, and you can say p times x plus 1, and you can say m equals p times x plus 1, where x is all the numbers until this, x equals all the numbers until this except p. You can say that exactly this is the same proof why p cannot be 2, 3 and so on until p. So since every prime number including p is a factor of of that product, q cannot be any of those primes. So this q cannot be any of those primes. So it needs to be a prime that is not included in 2 to until p. So q cannot be any one of those. Cannot be any one of those. Q needs to be an independent identity, and q also needs to be greater than p. That's how you prove it, that there is a number bigger than all these set of numbers until p that divides m. So q will divide m. It is bigger than p. That's how you prove there is always a bigger prime. Ah, that was hard for the first time, but if you take a look at it back again, it might answer your questions. Now I'll move on to take a look at mathematical induction. So, what is mathematical induction? The thing we did just now was a proof technically by the idea of induction. If 2 doesn't work, 3 doesn't work, generalized q doesn't work, so none of will work. Now, the principle of mathematical induction says that if there is a set called S, if S is any set, to be honest, in natural numbers with some properties, with the properties as follows. Number one property would be 1 is in S. So 1 is contained in S. You can say that. And the second property needs to be. So these are the requirements for mathematical induction to work. It's a tool. It's not something you can use as a statement or theorem. It's a tool. So 1 is in S, and there is k plus 1 is in, what is k here? I'm saying k plus 1 is in S whenever k is in S. What basically this means is that if you find a random number k in S, for example, you take 5, you should have a guarantee of 6 in this set. So, which is generally the case. You cannot take a number like 0.5 because 0.5 does not belong in natural numbers. So 1 plus 0.5 does not belong to natural numbers. Now, how do you use this mathematical induction? We'll take a look at how you use mathematical induction to prove some theorems. Is that you can take a very generalized question, which is the sum of, this is called the sigma notation, the sum of the squares of integers from k equals 1 to not infinity to n is always supposed to be this formula. So how do you prove this using mathematical induction? To prove this using mathematical induction, you have to keep in mind of the fact that there is a well ordering principle, which says that every set of natural numbers, contains at least one element that has the smallest element in it. But it doesn't work on this one, but it's fine. You can say this in one. So this is the sum. Now you need to prove this until n. Oh, sorry. Yeah, so if you have to prove this statement, so first of all, write this as until n. This is the statement we need to prove. N times n plus 1 times n plus 2 divided by 6. This is the formula we need to prove. How do you start? The first step was to prove this for, this is P. This is the property of P. So P equals this. Now you need to prove P for 1. P of n is this. So P for 1 will be, you just take 1 square, which will be 1 times 1 plus 1, 1 plus 2. You can take this as the left hand side of the equation. You take this and you take this, compare both of the values, this by 6. And if you uh, take out the value, which will be 1 times 2 times 3, which will get cancelled, which will give you 1. So this is proved for p equals 1 is p equals 1 is true, to be honest. You can just say that p equals 1 is true. So if p equals 1 is proved to be true, now you can move on to the generalized statement of pk. You have to take pk to be true to prove p of k plus 1 belongs in to be true. So p of k will be 1 plus 2 plus dot 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 dot, dot until k squared, and this is also as k times you'll have to write this as p of k equals this. So p of k is written as 1 plus 2 plus until k square, and you take this statement as true. Now you move on to prove using this that p of k plus 1 is also true. Now you need to compare both of the sides for p of k plus 1. You take this statement of k plus until k plus 1 and you take this statement to be true too. So 1 plus 2 plus 3 plus dot 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 dot, dot until k plus 1 whole squared. Until k plus 1 whole squared, and you take the other side, which will be k plus 1 times k plus 2 times k plus 3 divided by 6. The proof of the statement 1 squared plus 2 squared plus 3 squared plus so on until n squared gives you the value of is equivalent to the value of n times n plus 1 times 2n plus 1 divided by 6. So for proving this using mathematical induction, you'll have to prove it for p equals 1. This is p of n. P equals 1 would be proved as 1 squared, and you have 1 squared is from this. You put n equals 1 and you put yn equals 1 for this. So you get 3. This gives you 1, which is proved for p equals 1 equals 1. So p equals 1 holds true. It's true. Now you need to take p equals k to be true and prove using that p of k plus 1 is also true. I'm using the arrows in a very weird way because arrows generally mean implication, but it's not in that sense in here. P equals k is true. You can write is true to prove using that to prove p equals k plus 1 is also true. So how do you prove use p of k plus 1 is that you can mention p of k. What you can write as p of k will be 1 squared plus 2 squared plus so on until k squared. This p of k is also equals to k times k plus 1 times 2k plus 1 divided by 6. Now these two statements are true for you. Now you have to use this to prove the next step. So p of k plus 1 will be p of k plus 1 will be 1 squared plus 2 squared plus so on until k plus 1 whole squared. And you have to write on the right hand side is that this thing is the same thing as k plus 1, k plus 2, and 2 times k plus 1 will be 2k plus 3 by 6. So you can take this statement where you have 1 squared plus 2 squared until k squared, and you take one more statement in this, one more number, which is k plus 1 whole squared. You try to get to this from here. You now know that this part of it, which comes from p of k, so p of k plus k plus 1 whole squared is p of k plus 1. If you use p of k, which is the sum of all the squares of the natural numbers until k squared, you can write as you can add one p of k plus 1 as 1 squared plus 2 squared plus until k plus 1. You know, until k squared is the value is k times k plus 1 and times 2k plus 1 divided by 6, and you add k plus 1 to it, k plus 1 squared to it. Now you have to get from here to here somehow. How do we get that? We can start to do basic forced bash it. So you can just start by using k times k plus 1 times 2k plus 1, and you add the fraction divided by 6. So this will give you a common factor of k plus 1, which is k times 2k plus 1 plus 6 times k plus 1 divided by 6. This will give you k plus 1, and this is 2k squared plus k plus 6k plus 6 divided by 6, and this will give you k plus 1. We somehow got this k plus 1. We have to need to prove that this part is equal to this. So you can take this as 2k squared plus 7k plus 6 by 6. Notice how 2k squared plus 7k plus 6 times k plus 1 can be factorized with this to be as k times 2, k plus 2 times k, 2k plus 3, because 2k plus 2k squared plus 7k plus 6 is can also be written as 2k squared plus 6k plus k plus um, oops, yeah, it can also be written as 2k squared plus so 12 4k plus 3k plus 6. Now 2k squared, 2k can be taken common, k plus 2 times 3 times k plus 2. You can factorize k plus 2 times 2k plus 3. So this is equals to 2k squared plus 7k plus 6. So you can replace this value to be 2k times 3 times k. You can replace this with this value, k plus 2 times 2k plus 3 times k plus 1, which is proved here to be true. That was mathematical induction. The whole takeaway of mathematical induction is that you take p of 1, check if it's true. If it's true, if and only if it's true, move on to p of k, consider it to be true, and then try to prove from there that p of k plus 1 is true too. If you can do this, you can prove any generalized formats of equations. For example, sum of n from equals to 1 to k, you can prove that those two, k into k plus 1 by 2. You can also prove those values. which is called the Gaussian sum. Yeah. So moving on to the last part of this is the complex numbers. So complex numbers are the last part of types of numbers before you have transcendental numbers and other types of numbers that are not part of any kind of syllabus in high schools or colleges until now if you don't have maths as your major. So the easiest type of numbers after complex numbers would be transcendentals, but yeah. So complex numbers. What are complex numbers? So complex numbers are considered to be uh, the last thing in this part of equation. Say if you have a quadratic equation, for example, x squared plus 1 equals 0. If you try to find the solution to this x such that x belongs real numbers, you will find very easily that there does not exist x such that x belongs real number and x squared equal plus 1 equals 0. It's a very generalized statement. So you can say that there is no x such that x belongs to real numbers and x plus 1 square equals 0, because it's very easy to understand that if you square a number and if it's in the real numbers, you'll always get it graded to be equal to 0, because for example, even if you take the negatives, so minus 1 squared will give you 1, minus 7 squared will give you 49, minus pi squared will give you pi squared. So it goes on like that. It goes on like that. There is no real number you can square and get it to be equal to minus 1. So this implies that x squared equals minus 1, which is that does not exist simply. So you have to start to define another set of numbers which can solve these kind of problems. Those type of numbers are called the complex numbers. So that does not exist. So you have to define x belongs complex numbers. You're defining another set of numbers, and that is much bigger than the real numbers. If this is the real number, this is the complex numbers. Why are complex number bigger than real numbers? That's a question of different day, but I can explain it to you right now. So how do you solve this? So x squared equals minus 1, and you take it to be x squared equals x equals square root of my negative 1, which looks very ugly in the sense if you're working with real numbers. So you define it to be iota. Iota. Iota is only written without a title, but just for the sake of simplicity and it doesn't look like 1, it's written with that sign. So iota means that it's a different number. The definition of I is taken to be this. So definition of I is square root of negative 1. Why do or you can say definition of iota is I squared equals minus one. Rather use you can rather use this to be your definition. So iota is minus 1, the square root of minus 1. How do you use these kind of numbers? Any complex number, for example, any complex number, let's say x belongs complex numbers, and you want to define x, so x will be always of the form a plus iota b. So why a plus iota b? So this is called the real part of this x, and this is called the imaginary part of this number called x. Complex numbers complex numbers are generally written with z, so you can write it with z. You'll find this as in the books. You'll find this in the books, and other than that, this is you can write real part of z is a, imaginary part of z is b by definition. Notice how if you square this number, you'll get a squared plus, and you have to square this number too, plus 2 times iota AB. So if you square this, minus 1 times b squared plus 2 iota ab. This is not your standard a plus b whole squared. This is a plus iota b whole squared. So this iota squared gives you a negative in front, not a positive sign. Now every complex number z also has a counterpart, like a counter villain to it, which is called the conjugate of complex numbers. What are conjugates? So conjugates are if you just replace a and with the iota with minus iota, negative iota, that's the complex part. That's the conjugate of the complex number. So for a plus iota b, the conjugate will always be a minus iota. If you have another number, let's say a plus c, so the real part doesn't change, only the iota will be changed with minus iota, negative iota. So what's so special about complex numbers? One speciality you notice is that iota squared is -1, which is not something you generally observe. So yeah, now so there are some complex. There are some numbers that you can add together. So like this, if you add them, you can never add the complex and real part together. So you have to separate them. You have to separate them. It's like adding the real parts with the real parts and the imaginary parts with the imaginary parts, and these things never interact with each other in general. You can draw a graph, and this is the real axis and this is the imaginary axis. So the real axis will have a in here and somewhere around is b. This is the number. So you take the amount of imaginary part is going up and the real part is going in the x-axis, so you get the real number to be the complex number to be somewhere here. That is the complex number you're pointing at. This is a plus iota. um, Now, what if you multiply the complex number with its conjugate? These are experiments you're doing. So a plus iota b times a minus iota b will give you a squared. And if you multiply iota with iota, that gives you a minus 1, but there is already a minus 1, so you get a squared plus b squared. And you multiply this with this, so this will give you a iota b, and notice how this will give you a negative of a minus iota b. These will cancel out, it will be left with a squared plus b squared. Now, what this a squared plus b squared is called the magnitude of this. Why the magnitude? So, the magnitude of the complex number generally defines the length of this hypotenuse of the triangle that you see here. So, this length is a, this length is b, the square root of a squared plus b squared. This length, if you square it, you get this value of magnitude. Oh, sorry, this is the magnitude squared. So if you square root the magnitude, this will be the magnitude. Now, so there are some questions you can ask, like how do you define this triangle? So whenever there are triangles, there are angles. So how do you define any trigonometric ratios in here? Yeah, there is a very standard approach as to how you can write this. So for example, if you write this as r, so from this diagram you can write to be sine of theta as b by a, and cos of, oh sorry, b by r, and cos of theta as b a by r. Now this r is redundant, so if you wish to remove it, you can write as r sine theta equals b, and r cos theta equals a. Now you can write this in terms of this, so you can write r, which is the a part, so r cos theta plus r sine theta, or and add the iota sign in front of it. So this is the symbol for z. You can also write this is called the polar form of it. Take r common, it's cos theta plus iota sine theta. Whenever you go to Euler's formula from this part will be the Euler's formula. Euler's formula can reduce this to this form. What this basically means that there is a number which has a theta angle from the origin. This is the theta angle, and you need not define with these two numbers. So r e to the power iota theta is here as a plus iota b. These are interchangeable, where sine theta equals b by r, and but sin theta equals b by r and cos theta equals a by r. So this is another definition. These are interchangeable forms. This is the standard form. This is the polar form. Now, moving on, you can do the same thing with the complex numbers. Every complex number also has a complex root. So how do you find the root of a complex number? Okay, so since it's a square number, since it's a number, you have to write it as the way just now we saw, iota sine theta. Now, if you wish to square root this, you have to say this as there's always a number. It's in the polar form, so you can change this into the polar form, and you can put in the value of half in it. So let's say there is a w which is equals to square root of r cos theta by 2 plus iota sine theta by 2. And now if you prove it, if you do square of this, you'll obviously get back to this. How does this work? Well, if you want to prove this can be proved using a formula or a theorem called De Moivre's theorem, which says that r times cos theta plus iota sine theta to the power n is r to the power n cos of so what basically happens is that this r gets distributed between these two things. You can just write this as r times e to the power iota theta whole to the power n. So this becomes r to the power n iota e to the power n theta iota n theta. Now you will write this as, now you will expand this as n theta, not as only theta. So this will become cos of n theta plus iota sine n theta. So if you put n equals half, you will get back to, which is, you see, is half. All right, that's, I guess, we're done with complex numbers introduction. We'll see when we can move on with the following things like argument of complex number, which also behaves as a logarithm. But yeah, moving on, we can also talk about how we can find the nth roots of unity, which basically means that, for example, there is a complex number which is you can find what's a number that you have, and you can literally like say, if there is a number which is r to the power 4 equals 1, so what are the values of r? So obviously r can be minus 1, can be 1, but there are some more numbers you can say that will also be equals to 1. For example, iota can be 1, iota my negative. So there is also one this important things is that if a to the a plus iota b is a solution to some quadratic equation or a equation, a minus iota b needs to be the solution. they always form a conjugate pair. So they will always be in pairwise forms. So if one of them is a solution to it, the other one will also be. So the nth roots of unity follows from the fact that for each natural number n, the complex root of 1, the complex roots of 1, so n equals 4 here, so nth root of n, the complex root of 1 will follow the formula of cos to the power 2 pi plus 1 plus iota sin to the power 2 sine 2 pi by n. And you can generalize this format, but it goes on like this: 4 pi and dot dot dot, and the next one will be cos 6 pi dot dot dot, and so on. I can generalize the nth roots of unity as r equals r to the power n equals 1. So r has a generalized solution of cos this by n plus iota sine 2 pi n minus 1 for all for all you can write this as r. Actually, this will help you find the solutions for all n. R belongs from 0 to n. So you generally put like every value from 1 to n, and you get like r equals r equals 1 will be on a solution, r square plus 1 whatever the solutions are, where r will be negative and positive 1. If r cube for example will give you a complex number 1, uh, r cube equals 1 has a very interesting solution. 1 1 minus 1 cannot be a solution, omega and omega squared, you can write them too. So that was for today. We'll see when I can stream next. Thank you so much.